slides for Chapter 3. You can find these PDFs of the lecture slides in your Week 2 module. I strongly encourage you to print out the lecture slides, and then you can take notes on the lecture slides as we go through them. So again, just pointing out that the suggested reading, which when I say suggested, what I really mean is you really should read these things. We have here sections 3.1 through 3.7. Pretty much everything in there falls under that prerequisite topics that we posted in Week 1 module. So I'm not really going to focus on any of that material, and I'm going to spend more time focusing on 3.8 through 3.11. Again, you may have covered some of this in your Chem 152 class or whatever prereq you took prior to coming to Chem 200, but we're going to go into a little more detail with it today. So again, this is just a quick, dirty review of the prereq materials. The full list of prerequisite topics that you need to be responsible for knowing about is in the Week 1 module, so you should definitely go look at that. So again, items from Chapter 3 you should be okay with. What is a mole? What is it? What does it represent? You know, what is the number that represents a mole? Hopefully you know what that is. You should be able to determine the formula of an unknown compound. Again, if you need help with any of these things, I strongly encourage you to reach out to me, especially before our exam, which is on August 31st. So exam 1 will be chapters 1 through 3. So that's coming up, and that will be done during our synchronous time. So if you do have questions, let me know. Today, we'll talk a little bit about balancing chemical reactions, which you should know how to do already, but we will bring that topic back up again. And then we're going to talk about calculating, amounts of things based off of reactants and products. So this will be a little bit of limiting reactants, a little bit of like dimensional analysis review, things like that. There are a ton of great additional video resources at the end of the Week 2 module to help with all of these topics. So while I'm not going to be grading you for looking at these, they are very useful and will help guide you if you are struggling a little bit. So again, real quick, the mole, not the fuzzy creature, right? It's a counting number. So just like in our day-to-day lives, when we're comfortable with the idea of a dozen, if I say I have a dozen markers, or a dozen cars, or a dozen children, you all know I'm talking about the number 12. Obviously, in science, particularly in chemistry, we work with really big numbers and really small numbers. And that's where Avogadro's number, 6.022 times 10 to the 23, comes into play. It's a counting number, so you always need to have units with it. Is it 6.022 times 10 to the 23 particles? Atoms of carbon? Atoms of hydrogen? Moles of Al2O3? You need to have a unit associated with it to kind of drive the process, especially for when you start doing your dimensional analysis and your unit conversions. So I want to talk real quick in terms of looking back at molar mass, number of molecules, that kind of thing. So using the mole conversion. This is a problem straight out of your book. Again, when you read this section, hopefully you're following through with it. I just kind of wanted to walk through it with you. So isopentyl acetate, here's the formula, is a compound responsible for the scent of bananas. It's also released by bees in about 1 microgram when they sting. And this compound smells, and that's kind of a hint to other bees that one bee has already stung something and that other bees should come and sting the same thing. So the question is going to ask us how many molecules of isopentyl acetate are released in a typical bee sting. So we're going to go with this is a typical bee sting right here. And then off of that, how many carbon atoms are present in that typical bee sting. So there's a couple things we're going to need to solve this. We're going to need to calculate the number of molecules. How many of these C7H14O2s there are in 1 microgram of this material, and how many carbon atoms are in that 1 microgram. What do we already know? Well, we were given a formula, which means we can get the mass of this, right? We can figure out molar mass. And we know that a typical bee sting is going to be 1 microgram, or 1 times 10 to the negative 6 grams. So where are we going to go from here? This is a part of our synchronous video that hopefully you've already watched. So I'm going to, if you want, give you a moment to pause this video, go back and look at the synchronous video from week 2 and watch that. Otherwise, I'll pause for a minute and then we're going to keep on going from there. Okay, so now that you've watched the video on molecules, moles, molar mass, dimensional analysis, hopefully you're feeling a little more refreshed with those topics. I'm going to quickly touch upon some balancing chemical equations, give you a couple examples to look at, but again, this is mostly prereq, so we're not going to really spend a whole lot of time on it. We know when we have a chemical equation, right, this plus A plus B plus C yields D, E, and F, or something like that, that we have to have the equation balanced. So we may just know something like this: methane plus oxygen yields carbon dioxide and water. And that's a good starting point. However, when we start looking at it, I see I have 1 carbon on this side, 1 carbon on this side. I see 4 hydrogens on this side. I only see 2 hydrogens on this side. And I see 2 oxygens on this side. And I see 3 oxygens on this side. So I know this is not a balanced chemical reaction. The problem with that is we've kind of broken the law of conservation of mass, right? We somehow magically went from only having 2 oxygens to somehow having 3 oxygens over here. So if we were to look at this unbalanced chemical equation, we would just say another oxygen atom appeared out of thin air. We know that's not the case. So we have to go through and balance the chemical equation. And the best way we can do that is by balancing the coefficients. Remember, we cannot change O2 to become O3. That would be a different material. That wouldn't be oxygen anymore. It would be ozone. So what we can do is say, well, I can have 2 molecules of O2 is how I can change it. So we can only, when we balance chemical equations, we can only change coefficients. That's the number in front, not the little subscripts. Again, when we're writing a balanced chemical equation, don't forget your states of matter. They are very, very important. They actually do count. They do count for points. They count in being able to tell us what materials we have, what state of matter they're in, which will be important to us later as well. So here you have 2 chemical equations that I'm going to pause. I recommend you pause the video and actually try balancing these out. All right, so when you do so, we should end up with 3 calcium hydroxides plus 2 H3PO4 yields 6 waters and 2 calcium phosphates. And for B, we end up with 2 silver nitrates, 1 H2SO4 plus 2 HNO3s, and 1 silver sulfate. And again, remember, we have only changed coefficients. Now, if you're someone for just kind of bookkeeping purposes that needs to put a 1 in front of something like this, that's totally fine, totally acceptable, not a problem. But make sure you have states of matter, just like when you take a measurement and you have to have a unit like grams or centimeters or degrees Celsius or whatever, you need to say what state of matter you are in. So the next practice problem that we have, again, this is still 152 review, is kind of using amounts of reactants and products, playing around with some dimensional analysis. Again, for this, I have posted in the week 2 module a written out with very detailed instructions solving of this equation. So I would really encourage you to stop right here again and pause the video and try this out on your own. Obviously, this is an online class. I can't force you to work on this problem and kind of just stare at everybody while you're quietly standing there until you work on a problem like we would in a face-to-face class. So you may just be like, yeah, I know how to do this, and move on from it. But make sure you actually know how to do it. I really encourage you, pause the video, get out a piece of paper, go try this problem. See if you can get it right. If not, then go look at the answers. Or even if you do, see if there's anything you missed along the way. So once you've solved for it, hopefully you've found out that we have 7.24 grams of our aluminum, 21.4 grams of our iron, and the maximum amount of the aluminum oxide. Oops, sorry, I just realized that should be subscript right there. Typos do happen. We can only make 13.7 grams of aluminum. All right, on to some new concepts. The first thing we're really going to start talking about in Chapter 3 that's new is this concept of a limiting reactant. So in the previous problem, you were given the amounts of both reactants. We knew that we had, something like 7.24 grams of aluminum and 21.4 grams of the iron 2 oxide. Or excuse me, iron 3 oxide. So whenever we have given amounts of more than one reactant, the thing that is on the left-hand side of the yields arrow, you want to start thinking limiting reactants. That's where we're going to start going with this. So up until now in your chemistry classes, we've assumed that reactants are present in the correct amounts that we need to react completely, everything's beautiful, all that kind of stuff. In reality, it's a little more complex than that. Oftentimes in a chemical reaction, there's one reactant that is in excess, or one or more reactants that are in excess, and only one of them is going to be the one that limits the amount of product that can be formed. And just like the term states, limiting reactants are completely used up in a reaction. That means at the end of the reaction, whichever reactant was the limiting reactant, there's now no longer any left over. There's 0 grams left of it. The reactants that are not limiting are the ones that are in excess, and therefore there will be some of it left over. So the example your textbook gives is making ice cream sundaes. And this isn't you sitting in your, kitchen having a pandemic snack and being like, I'm going to, see whatever's in the fridge, whatever's there, I'll make it happen. This is like you work at McDonald's and there's a very specific recipe that we have to follow. So for our sundae recipe, you have to have 2 scoops of ice cream, a cherry, and 50 milliliters of syrup. That makes 1 sundae. So if these are all the materials I have, how many sundaes can I make? And what is the limiting reactant? Well, if I looked at just the ice cream, I would say I could make 1, 2, 3, I could make 4 sundaes. If I looked at just the cherries, I could make 1, 2, 3, 4, 5, 6 sundaes. If I looked at my syrup, I could only make 2 sundaes. So the reactant or the ingredient on the left-hand side of the yields arrow that limits the amount of product that can be made, in this case, is the syrup. So we can only make 2 sundaes. The ice cream and the cherries are left over. They're in excess. So, like we said, limiting reactant will be the one that runs out first and then limits the amount of product that can be made. So in the previous example, we ran out of chocolate syrup. So that was our limiting reactant. To determine how much product can be formed from a given mixture of a reaction or of reactants, we have to look at which one is the limiting reactant. So what I mean by this is what I had said earlier. If you are given a word problem or something like that, where you are given amounts of more than one of the reactants, your brain should always go, uh-oh, this is a limiting reactant problem. So some mixtures can be stoichiometric, right? We know that all the reactants will run out at the same time, and because of that, right, it determines which one is the limiting reactant. So how are we going to figure this out? We're going to go through a problem where we're going to figure out the limiting reactant. There are 2 different ways, 2 different processes that are both correct. It really will depend on the information provided to you in the question. You can either compare moles of the reactants to figure out which would run out first, or you consider amounts of products that can be formed, and that will determine limiting reactant. In your homework for this chapter on OWL, you will have both ways to solve for it, so you'll get practice with both. Solving a limiting reactant problem. So here we're going to go through a word problem. We're going to start getting more familiar with the idea, right? We're at a 200 level class now. Be comfortable with seeing things like this. This is why nomenclature was a part of your prerequisites. We're going to start moving away from this idea of giving you the formulas and that you're going to have to take the word problem and turn it into a chemical equation. So we have nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. Other products in the reactants are solid copper and water vapor. And then the question goes on to say, if a sample containing 18.1 grams of NH3 is reacted with 90.4 grams of the copper oxide, copper 2 oxide, which is the limiting reactant, how many grams of N2 will form? There's a lot going on here. The first thing we're going to need before we can do anything else is a chemical equation. So, as we go through this, I really encourage you to stop at each step and try writing it out on your own first. So let's go through bit by bit. We're told, okay, nitrogen gas can be prepared. Well, if it's being prepared, that would mean that nitrogen gas has to be one of our products. So I have N2 because nitrogen's diatomic, and it's a gas, so I'm going to put its state of matter. It can be prepared by passing gaseous ammonia, here's ammonia, gaseous state, over solid copper 2 oxide. Copper 2 oxide, solid, at high temperatures. So if you want to put a little triangle up here to represent delta for a change in heat, you can. Other products in this reaction, so other products, things that go on the right-hand side, are solid copper and water vapor. So we know when we see vapor that that's a gas. So this is water in its gaseous state, or steam. All right. First thing you should always do whenever you see a chemical equation before you do anything else is always check to see if it's balanced. So when I do a quick assessment of this, I see 1 nitrogen on this side, 2 nitrogens on this side, nope, not balanced. Let's see, 3 hydrogens, 2 hydrogens, nope. 1 copper, good. 1 oxygen, 1 oxygen. All right, so we definitely have some balancing that needs to occur here. I would encourage you to stop the video right now and try and balance this equation before continuing. All right, so when we balance the chemical equation, we find that we have 2 moles of gaseous ammonia plus 3 moles of copper 2 oxide produce 1 mole of nitrogen gas plus 3 moles of copper solid and 3 moles of gaseous water. Now, if we take this sentence right here and kind of write it out next to our balanced equation, we end up with this. We know we were given that we have this much of this reactant and this much of this reactant, and that we want to know how much of this gets made from that when we mix these two together at high heat. Here's your hint. We have 2 reactants with amounts, so this is going to be a limiting reactant problem. I'm going to show you how you could solve for this utilizing just one of the methods. Like I said, on your homework you will have the opportunity to do it based off of moles of the reactants as well as based off of amount of product made. So whenever we're given grams of things, 99.9% of the time, you won't be able to do anything with it. We need to convert these to moles first. So go ahead and convert, the 18.1 grams of the ammonia and ammonium gas and the 90.4 grams of the copper 2 oxide into moles. Again, pause the video, try this out on your own. Okay, so we need the molar masses of both of our reactants, and then we can go through and do dimensional analysis to identify that I have 1.06 moles of NH3 and 1.14 moles of our copper oxide. So now I'm in moles. And I'm asked, right, one of my questions is, how much nitrogen gas can I produce? Now, when you're doing a limiting reactant problem, look at what the overall problem is asking for, because sometimes, you know, solving for one product is more useful to you than another. But we could do the same problem solving for copper or the water, and we would end up with the same process. and the same results in determining which one of these is the limiting reactant. However, whatever you use for one of them, you have to use for the other. So what I mean to say is, if we're going to solve for a product, we have to use in both situations the N2, or in both situations the copper, or in both situations the water. So we're going to solve based off of the N2 because that's what we're asked about. So we can solve for moles first. So at this point, I would encourage you, just like we did in the example that was posted that I wrote out, where we went through and we said, okay, I have to now solve for both givens. Go ahead and use 1.06 moles of NH3 as one of your givens to solve for moles of N2, and then do it again for 1.14 moles of the copper 2 oxide. So when we do that, we find out that the ammonium gas can produce 0.530 moles of N2, and the copper 2 oxide can only produce 0.380 moles of N2. This is important. So we know that a limiting reactant limits the amount of product that can be made. So based off of that knowledge and what we got in our calculations, which of these is the correct limiting reactant? The copper 2 oxide or the NH3? Hopefully you've determined that the copper 2 oxide should be the limiting reactant. It produced less NH2. Under the conditions given here, we can never produce 0.53 moles of N2. We would run out of copper oxide before we would be able to get to that 5.3. Or excuse me, 0.53. So this is our limiting reactant. Now, the last step was they wanted it in grams, so you would take this number of moles of nitrogen and convert it to grams. We end up with 10.6 grams of nitrogen is all we can form. All right. The last topic what we're going to kind of talk about in this chapter is the concept of yield. This is something that will be very important for lab, but we also do use it in lecture. The tricky thing here is, oftentimes when we're dealing with theoretical and percent yields, a limiting reactant problem will sneak into here. So a sneaky way of being asked about a limiting reactant problem would be giving you a percent yield or a theoretical yield. So what is a theoretical yield? What is a percent yield? Theoretical yield is the amount of product formed when the limiting reactant is entirely consumed. Now, this makes sense, and you're like, well, that should always happen. But there's a difference between what happens in the real world, in lab, and what happens in our textbook. So obviously you've all been in lab before, hopefully. And I know this semester we are in electronic labs. But for the most part, you know that things happen in lab. Maybe you spilled a little bit of material when you were collecting it, or you weren't able to scrape every last little bit out of the bottom of the beaker, and therefore the amount of product that you collect at the end is probably not the same as what you would get if you did the math on paper for the reaction. So that math on paper, the perfect, everything went great reaction, the math on paper, is the theoretical yield. The percent yield is what you actually collect, right? That amount that you collected after you scrape the beaker, right? There's still some left in the beaker, but the actual amount that you have that you isolated at the end. And that's a percentage of the theoretical yield. So we're going to use these concepts to go through the question I have over here. Methanol, CH3OH, can be manufactured by combining gaseous carbon monoxide and hydrogen. In a certain reaction, 68.5 kilograms of carbon monoxide gas is reacted with 0.86 kilograms of hydrogen gas. Calculate the theoretical yield of methanol, and then we go on to say, in this reaction, right, if 3.5 times 10 to the 4 grams of methanol is actually produced, what was the percent yield? All right, so there's a lot going on here. So we're going to break it down bit by bit. Just like last time, the first thing we need to do is write a chemical equation. So I'm going to give you a moment right now, pause the video, write out your chemical equation. All right, so I know that hydrogen gas and carbon monoxide gas have to come together to make methanol. Always, 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 whenever we see a chemical equation, what's the thing we should check first? Is it balanced? So go through and check to see if it's balanced. If it's not, pause the video and go through and balance it. It was not balanced, right? We had too many, or not enough hydrogens. So now we know that for every 2 moles of hydrogen gas plus 1 mole of carbon monoxide produces 1 mole of methanol. And look, when we go through the problem, as it was given to us, we found out, we have 2 given amounts for our reactants. And we're trying to find out how much of this can be made. This sounds like a limiting reactant problem to me. So we're going to go through all those steps again that we did with the previous example, and then at the end we're going to add in the yield portion. So we know that grams, or in this case kilograms, are pretty useless to us and that we have to get into moles first. So go ahead and convert our givens into moles. So pause the video, go through and do that. All right, we have our molar masses, we go through and we convert, and we end up with this many moles, 4.27 moles times 10 to the 3 of our hydrogen gas, and 2.44 moles times 10 to the 3 of our carbon monoxide. So now we can use these moles to solve for our want. So go ahead, and you're going to have to do this twice. You're going to have to set 2-dimensional analysis reactions, or equations. One using carbon monoxide, the given amount of carbon monoxide, and one using the given amount of our hydrogen 2 gas. When we do that, we end up with something like this, right? We're going to go through and do our dimensional analysis, and we find out that the carbon monoxide, if we were to go with that as our limiting reactant, would produce 2.44 times 10 to the 3 moles of methanol, and that the hydrogen gas, in its quantity, would only produce 2.14 times 10 to the 3 moles of methanol. So when we look at this, we want to go through and go, which of our reactants, this one or this one, limited the amount of product, this one, we can make? The H2 produce less product. This makes it the limiting reactant. So in theory, if we ran this reaction in the lab, in a perfect world, this is how much methanol we would make. But we only made this amount. And your gut might be like, well, this is more than this. But look at what we have here, 10 to the 4, 10 to the 3. Excuse me. So what we need to do is take our theoretical yield, which is this one, and we're going to determine that the grams, oh sorry, you may still be confused. That was not me explaining things very well. This is in moles, 10 to the 3 is in moles. We need to convert this into grams to compare with the 10 to the 4 grams that we have here. Sorry about that. That was me not explaining things clearly. So if we have 2.14 times 10 to the 3 moles as our theoretical yield, if we converted that into grams, we would end up with 6.86 times 10 to the 4 grams of methanol. This is our theoretical yield. In actuality, we only produced this much methanol. So we want to figure out our percent yield. To do percent yield, we're going to take the actual yield, which would be this guy right here, and we're going to do that as a ratio of the theoretical yield. The theoretical yield was what we had based off of our limiting reactant, converted into grams. So actual divided by theoretical times 100. Now, when you're doing sig figs for this, The 100 here is a percentage, so it's an exact number. So it won't contribute to determining number of sig figs. These guys over here do. So we have 3 sig figs and 3 sig figs, so our answer can only have 3 sig figs. Go through this, try it on your own. I encourage you, after we walk through it, try write it out again on your own. Like I said, your homework will have a lot of good practice with this as well. So lastly, let's look ahead at week 2, what's coming up, even beyond a little bit. Please go read chapter 3 of your textbook. The first slide in this lecture has the sections that you should be comfortable with. If there's any material that you need clarification on, please ask me. We are at a 200 level class now. We expect that you are able to read some of the textbook on your own, and the less complicated concepts, we're letting you kind of, feel out for yourself. Now, in the OWL homework, I do add questions based off of the reading so that you get practice with them to kind of know where you're at. However, if there's something you don't understand about the reading, I'm expecting you to reach out to me and ask a question. Please, please, please ask questions. You should be working on your OWL assignments as well, okay? So chapter 3 OWL homework is up. Also, we will be having one more, quote unquote, whatever you want to call it, practice quiz. So even though we're calling them practice quiz, they still are worth full points. But it's basically like free points for you. So the quiz 2 was a practice quiz, right? That was the one where I was like, what's your name, right? What comes after the letter G or whatever, right? It wasn't content based. It was just to help you learn how to use Proctorio. We're going to have one more quiz like that, and what it's going to be is going to be going into Cengage through Canvas while using Proctorio. So it's like the turducken of like an assignment. And so quiz 4, which should be released on Thursday, will give you some practice with that. And it's really important that you do quiz 4 before our exam 1 on August 31st, because exam 1 will be using that turducken kind of assignment. Okay, so I want you to not be stressed out on exam 1. I want you to have already experienced how we go through getting into Cengage with Proctorio and all that kind of stuff. I want you to know how to do that before the exam. That way there's no stress on the exam with trying to get into the software and everything not working and all that. I want you to just be focused on the material. And lastly, after all the lecture stuff at the bottom of the week 2 module, I have a lot of worksheets. For certain sections in our text, as we go through the semester, I'll have practice worksheets. And basically, I would encourage you, print out the worksheets, the blank ones, and actually go through and do it. And then I've also posted the keys for everything. So then you can go and check your answers, looked at everything worked out. The keys have, full descriptions of everything that's going on in them. Again, if you have a question based off of a practice worksheet, let me know. I'm happy to go through it with you. And as I said, there's also YouTube videos at the end if you're looking for additional resources there. So I mentioned it a couple times, but please keep in mind our first exam, exam 1, is going to be on August 31st. It will be during your synchronous time, okay? You will have the whole 85 minutes. So on August 31st, there won't be anything else to do during the synchronous time except take the exam. Now, for the rest of the week, you'll still have stuff to do, but you won't have anything else to do for the synchronous time. If you come late to the synchronous time, you don't get extra time at the end. Just like if you were in a face-to-face class, if you came 10 minutes late to class for an exam, you lost those 10 minutes to take the exam. If you have any issues, please let me know. All right, that is the end of our first narrated lecture video where there's new material. If you have questions, like I keep saying, please reach out to me. Work on your homework, do the reading, do the practice problems. It's all going to be good. All right, have a good day.